course, we used PLL for feed-forward term here and also for the reference current. So we discussed the PLL in details. We discussed how to limit the current also. Next and the last step would be to design K1, K2, and K3, the controller design, which by now it should not be difficult for you to do. Just writing down the equations. So equations of the resonant controller, this is X1. It has two state variables, right? So if you write down the state equations, will be, this is one of these equations, and this is the second one. So always you need to write down the state space equations of controller. If it's an integrator, it's very simple. If it's resonant controller, it will give you two equations. Now you need to combine these two equations with the equations of the plant or converter, which is only one equation. So this is the equations of the controller, and the equation of the plant is this one. For the current. So X3 is current, X1 and X2 are the state variables of the resonant controller. So based on this definition here that we just gave, you can derive these two equations as well. Okay, keep those in mind. We'll use them in a moment. Now, we combine these equations all together. So these are the equations of the controller and plant together. So we'll be in state space form, x dot equals ax plus bu plus bref iref plus bg h. Names, I use G for grid, H is for harmonics, and then Y is Cx. A is this one, B is this one, B ref is this one, so a standard format. And controller is negative K1 x1, negative K2 x2, negative K3 x3, so negative Kx. Okay. Controller has no problem, it's full state feedback. However, if you look at these equations, we have terms like this. And this also, which actually prevent us to say this is an LQR problem. We need to remove them. If you want to remove them, H is harmonics, but IREF is a fundamental. So in general, if harmonics and fundamental at the same time you want to remove, it will be complicated. Let's start simple. Assume that harmonics are not there, or really they are so small that we do not care at this point. We only have this term, sinusoidal at frequency 60, okay? Then if you apply this transformation to both sides of these equations, right? And also to this one. So to the control law and to the state space equation. And then define Z, Z1, transformed version, Z transformed version of X. So Zi is Xi double dot plus omega 0 to Xi. Now this transformation removes this one. And what you get is this set of equations. And for the control law, now let's call it W, becomes K1Z1, K2Z2, becomes negative Kz. Now safely you can say this is an LQR problem because you don't have anything else, and then you want to push Z1, Z2, Z3 to 0. So this is an LQR problem. We can apply LQR. So what is the cost function? The cost function, general form, is Q into error square, Q2 into error dot square. Why error and error dot? Because what is Z1? Z1 is this transformation applied to X1. And Z2 is this transformation applied to X2. Now look at this equation. This transformation applied to x1 is z1. So z1 is error. And z2 is derivative of error. So again, this is a nice thing about this approach is that error and derivative of the error appear in the cost function. And these are variables that we can feel, we can physically feel and work with. So error and derivative of error, they appear in the cost function. And the third one is not derivative of current. This is not correct. It should be second derivative of current plus omega 0 squared into current. Now apply LQR and then you find K. You only need to adjust Q, Q2 and Q3. Let's go with this setting, VDC 500 volt. On the AC side we have 240 volt AC, frequency 60 Hertz. This 240 is RMS. So peak value is, I think, 340 or something like that. So L is 5 millihenry, R is 30 milliohm, switching frequency 4 kilohertz, power rating 2 kilowatt. So we want to feed 2 kilowatt. Also reactive power rating, you need to define that also. Let's say plus minus 2 kilowatt. So we can have both sides, supplying reactive power or absorbing reactive power. And the current we want to limit at plus minus 22 amperes, peak of 22. So peak current should not go above 22. At the rated operation, let's say 2000 watt and 2000 var, the current is 16.7. So we want to limit at 22. So we will leave some margin and then say we want to limit at that. So we put the saturation block at 22 and negative 22. Okay, so what we do, like before, we start with Q1, we increase Q1 and we increase Q2, we increase Q3, all three together. And then we get a typical graph like this. And whenever we are happy with the location, we stay there. And these are the simulation results. In this simulation result, basically, it's grid connected. Now in grid connected and situation like this, when you want to start, this is the procedure you go. First you run the PLL, so make sure the PLL converges. And then at that point, after PLL is converged, you start applying the switching function. So at t equals 0, PLL starts. At 50 millisecond, converter starts. And let's say the set points are 0. So it starts at 0. Then you see a very nice almost no transient, very smooth start, because PLL already converged. We put 50 milliseconds for the PLL to converge. And then at this point, 0.1, we apply a real power, 2 kilowatt command. So immediately the converter generates a current such that 2000 watts is generated. At this point, we also apply 2000 watts. So it adjusts this current to provide 2000 watts and 2000 var. And then negative 2000 vars. And then back to 0. Okay? So these are the tracking things. We have real power and reactive power. All three, we tested them here. The other thing we need to test is the current limiting. For the current limiting, we can apply a fault to the grid voltage. So a grid voltage fault, I think, happens here at 0.3. The grid voltage fault, voltage sagged down to 30%. So the voltage deeply goes down to 30%. So the current tends to increase 3 times, but the controller limits the current. There is a little overshoot at the peak, but it goes back. See? So at 22 really limits that. Okay. So I think I'm going to show the simulation for this one. Let's first run the design. I can run only this part. Very simple loops. Every loop has one line and it generates the, okay, did I put it? Very simple and systematic. Yeah, it's supposedly running, but it's taking some time. There you go. Okay, so this is the design stage, and the simulation is here. Let me explain the simulation file also very quickly. So this is the power circuit here. Again, a full bridge voltage source converter. Here we have a DC voltage. We use controllable because we want to change that. We apply disturbances, even though I don't know if it did here. On the right side, we have one inductor and then one grid. You may want to add impedance here for the grid as well to make it more practical situation. And then this current you measure. If you want to look at the total harmonic distortion of the current, you can use THD in MATLAB, THD block at 60 Hertz. Then, but before, every time you want to use THD, make sure you use the low pass filter before that. Otherwise, what it does, it brings in the switching frequencies, switching noises into its calculation and gives you wrong answers. Okay, so here is the AC grid, and here I applied voltage drop in the AC grid and those things, so we use controllable voltage source. This part is the PWM, it's a unipolar PWM. This is the controller, which I reference comes here. There is a T start, because we want to wait a little bit and then start. So you need to define a start. So a start at that point multiplies in this one, and then minus the current. This is the resonant controller. It has two integrators, and then omega 0 squared, and then three gains, K1, K2, K3. And this is the feed forward term, you remember, from the PLL. And this is the division. But we divide by 500 because in this simulation, we put a battery on the DC side. We are going to do the capacitor later. Okay, there are two other things. One is the reference current generation and PLL. So this is PLL. I'm sorry it's a little messed up, but should be good, should be showing. This is the DC part, and this is the magnitude part, this is the phase part, and this is the frequency part. And this is the reference generation. The limiting is here. We limit at 22 and negative 22. And then you have two set points for one for real power, 0 to 2000, and one for reactive power, which we apply multiple changes for the set point. Okay. Now I can run this one. Okay, it's already running. Multiple signals you can watch and see what's going on. Yeah, sometimes it takes a long time to start. It's compiling. This one. Yeah. It's basically the grid voltage and the converter current and the reference current that is generated. So the yellow one, which has switching noise, is the actual current of the converter, and the blue one, which doesn't have noise, is the reference for the current. And I show a factored version of the grid voltage as this brown figure here. So you see the grid voltage drops to 30% during this time. And yeah, and the current is limited at 22. And then when it goes back to the normal, you will see a little higher. So the current limiting, I told you and I explained to you, is a challenge. We hardly, especially in AC, we hardly manage to completely limit the current. So this level of sometimes, for a very short amount of time, the current going above what you really designed. You should either manage, first of all, because the time is very small, switches should be able to tolerate it. Secondly, if it's not the case, your switches cannot tolerate, you need to make sure that the switches primarily when you purchase them, you purchase properly so they can tolerate that level. But I believe this amount of time should be fine for all the switches that we have. Okay, all right. So another class is 9. Okay. I'm going to open it right now because it takes some time to come up. All right. So we discussed the basic structure for the single phase AC grid connected, AC grid connected inverter. If it wants to follow the commands of real power and reactive power. Now let's discuss a few issues around this topic. One issue is the grid voltage harmonics. So harmonics exist in any AC grid, especially harmonic 5, 7, 11, those harmonics, even odd harmonics of some numbers, they are there. So if you really look at the transfer function from the grid voltage to the current, and you know the structure, the feedback loop structure that we had, and you calculate that transfer function, that transfer function becomes like this transfer function. And now if you show that transfer function, the magnitude of that transfer function with respect to frequency, that's this one without controller, and this is with the controller that we just placed. So this axis is frequency, this is 60 hertz, this is 100, right? And this is 1000, this is 200, 300. Now, 300 means the fifth harmonic. So at the fifth harmonic, which is often the first harmonic which is there. So you see open loop and closed loop already at the same point. So that means this controller cannot help or does not help with harmonics, does not mitigate the harmonics. What it does, it makes sure that at that fundamental frequency, the grid voltage as a disturbance is removed, treats that as a disturbance because we put a resonant controller there to follow the reference. That follows the reference, also removes the grid voltage as a disturbance, even though we put a feed forward anyway. So feed forward takes care of removing that disturbance. But even if the feed forward, the reason we use it is because we want to have a soft start and current limiting. But the controller, in long run, controller itself also removes it in the steady state. Okay, so now let's see these numbers I want to explain a little because it's important. This transfer function that we just discussed, let's say harmonic 5, we are here. The magnitude is negative 20 dB. Negative 20 dB means 0.1 non-dB. So output current to the input voltage, grid voltage, is 0.1. Whatever you have in the grid voltage multiplies into 0.1 and goes to the output. So let's say you have a harmonic 5, which has the magnitude of about 2%, very realistic to say, for this 248 volt RMS. So the magnitude is 4.8 volt RMS for the harmonic, right? So how much will be the current? 0.1 into 4.8 into square root 2, the peak of that becomes 0.57. Okay, 0.57 will be the peak of the harmonic 5 of the current. How much was the total current? Let's say at 3 kilo kVA, if you are operating, which is the peak, it will be 17.17. And then you divide this by this one to get THD. THD will be 3.2%. Now, if you go to lower power, let's say the converter is operating at 1 kilowatt, the THD becomes 10%. So a tiny amount of harmonic, as far as the voltage is concerned, right, 2%, it can generate huge amount of distortion on the current. Okay? DC is not very important because it looks like there is a lot of attenuation on DC. That's what I explained here. There is another point that you may have concern, the reference point. The reference point comes from PLL and other things. The transfer function from reference point to the output current also, you can study that transfer function. And then you will realize it will have a figure like that. And at harmonic 5, it will be 200, 300, 100, 500, negative 10 dB almost, right? Is it 500? No, 300, we should say 300, 200, 300. It's about this one. So if you have distortions in the reference current, that also will go to the output. But the reference current comes from PLL, so you need to make sure that your PLL is sufficiently removing the harmonics from the grid voltage. So 2 points in this system that provide input to the system. One is the grid voltage, one is the reference current. The grid voltage, you have no control over it, it's coming from outside. But the reference current coming from the PLL. If you design your PLL well, you can minimize the harmonics there. But the one from grid, you don't have control over it. It just comes in. How we can fix this problem? So the way to fix this problem, the standard way would be this one. We already talked about this controller. So we add these two. These are the new ones. DC and harmonics. For instance, this is just one example. If I want to make sure that the output current absolutely has no DC, output current of the converter, and absolutely has no harmonic 5, for instance. So I put one resonant controller at harmonic 5 here, and I put one integrator here. So this gives me one state variable, so I need one parameter, one gain, and this gives me two new state variables, K3 and K4. And the input to these blocks, this is important thing, the input to these blocks should not come from here. The input to these blocks should come from the current, from the output. That's why I put it red, because I wanted to emphasize on that. This comes from the current. Because for any reason the current is distorted, it should remove that harmonics. Okay, the design stage is very systematic. Just write down the equations, x1 and x2 for the main resonant controller, and the state space equations will be this one. Then you have harmonic n, let's say harmonic 5. Two more equations for harmonic 5. And then one equation for DC. And then one equation for the plant. All together will be 6 equations. And the controller is this one, negative kx. And A and B, A is this, B ref. So the next step is to apply the proper transformation. The proper transformation in this case, because we have fundamental, we have harmonic N, and then we have DC. So you have to combine all three together. So in that case, this transformation will remove all the additional terms from these equations. I ref and H, harmonic 5. Because we assume that now H has DC plus harmonic 5, so we want to remove it. Right? Okay. So we get to these equations which have no additional terms, right? Okay. And then we apply LQR. Okay, to apply the LQR, the cost function is what? The cost function is Q1, Q2 into error and error dot, derivative of the error. Now, in this, there is a little mathematics here I don't want to engage at this time, but it's showing that, because in the steady state, let me just explain the big picture, what's happening, but we don't need to go into details. So what we are saying is that here we apply a sinusoidal reference, right? Purely sinusoidal reference. And we would like our current to be sinusoidal. Sorry. If the grid voltage has harmonic 5, this also should have harmonic 5, right? So it should generate harmonic 5 such that this current becomes sinusoidal without harmonic, right? And then this error will become, there you go. Let me read the explanation because I forgot some of these things. It's been a while. But anyway, the idea is to define a modified error and then prove that this modified error and derivative of this modified error will be in the cost function. So in the cost function, we will have Z1 will be this modified error and derivative of this modified error. I don't remember all the details now, to be honest. And then we have a summation of all the others, like 3 to 6. They are coming from here, and then transformed version of the modulation index. Okay, now let's practice this in the context of this example. So for the same example that we had before, we are going to extend the controller for DC and harmonic 5 to make sure that if the grid voltage has DC or harmonic 5, the controller can respond properly without generating distorted current. So this is the situation. So now you have, how many poles we have? The matrix is it 6? Yeah. 1, 2, 3, 4, 5, 6, exactly. So we have 6 poles. So they move here when you increase Q, and then you stop at some point, and then you increase Q2, and then you stop at some point, you increase Q3. So you see the Q3 starts changing the poles of the harmonic. And then Q4 also the harmonic. So Q and Q2 are for the fundamental. Q3 and Q4 for the harmonic. And Q5 dominantly for the DC. Right? And Q6 also you can apply. It changes everything. So by just watching them, you can make sure that it has a good response. Let's see what where are the poles eventually. So these are the numbers for the K, and these are the poles. So I have two complex poles, two set of complex poles, and two real poles. So on the real axis we have two poles, and then we have 6 poles altogether. Okay. If you show the magnitude plots versus frequency, it confirms that at fundamental and harmonic 5 you have no output, so it actually removes them. Also DC, at DC also removes them. This is without those block harmonic 5 and DC, and this is with harmonic 5 and DC. Now, in this simulation, which I will run on the computer as well, the situation is that the inverter responses in highly distorted, which is 5% of the fifth harmonic and 15% DC. Because DC, you cannot see it. For that reason, I really increased it much so we can visibly see what's happening. Conditions. And at T equals 0.2, the harmonic unit is enabled. At T equals 0.3, the DC unit is enabled. So initially, up to 0.2, up to this point, these new blocks that we added are not there, are not working. So this converter starts, here it starts generating power, but the current, if you look at the current, you see the current has a lot of distortions on it, a lot of harmonics. And also if you watch it, it has DC, so it has both DC and harmonics. Then at this point, 0.2, we apply or we enable the harmonics block, the fifth harmonic block. So you see the current becomes sinusoidal. But still it has a offset. See, let's compare this one. It has a DC offset. And then when you enable the DC block, it's a little transient, but after that, the DC is removed. Okay, let me see if I can quickly run this as well. Okay, the code is very similar. So we have loops, multiple loops. Each loop takes care of one of the queues. Right? And these are for generating those body diagrams. I don't need to run them. Only I can run this part. This is when you increase the first queue, the second queue, the third one, and so on. So you see, when you increase some of them, the other poles may come back. So you always have a trade-off how much you increase queues. You should not do aggressive changes. Okay, the structure is the same except in the controller. You have one block now for the harmonic 5 and 1 block for the DC. Everything else is the same. So you see the grid voltage is distorted, and the inverter current is also distorted up to this point. And now at this point, the inverter current becomes sinusoidal. And at this point, the DC is also removed. And this is the situation that you decrease the grid voltage, current limiting, to limit the current. All right, so I think that's all about this one. Okay, so that was grid feeding, right? Because we feed this amount of real power and this amount of reactive power to the grid, and if there are harmonics, how to fix that problem. So we discussed these two. The second aspect, if our converter wants to provide support to the grid, what should we do? So again, support have two aspects of support: dynamic support and static support. And now here in AC, the waveform, AC waveform has two parameters: magnitude, phase, or magnitude, frequency, you can say. So you need to, and powers will be real power, reactive power. So in DC, we only have voltage and power. That's it. Voltage, real power. In AC, we have real power, reactive power, magnitude, frequency. So we need to combine or relate these two together. But the problem is there is no clear relationship between these things in AC. In other words, you cannot say for sure or 100% that frequency and real power are related together, or reactive power and magnitude are related together. In large transmission systems and big synchronous generators, that is to good extent valid. In other words, real power and frequency are related together, and reactive power and magnitude. But when you move away from this situation, you go to distribution system with lower voltages, more resistive lines. This is now no longer valid. So therefore, the approach that I'm going to use here, I'm going to say real power and reactive power, both of them are related to the frequency and magnitude combination of them. And that combination, in order to make that combination happen, I introduce a new variable or a new parameter, theta s, that can change from 0 to 90 degrees. If that is 0 degrees, let's say theta is 0, this becomes identity matrix. So P related to frequency, Q related to magnitude. And if it goes to 90 degrees, it becomes completely opposite. Now, this is a static support because power is related to the difference, is connected to the difference between frequency and the nominal, and the reactive power difference between magnitude and the rated value. So this omega g and Vg are the actual magnitude and frequency of the grid, and these are the rated values. And for dynamic, similar thing. So you can say, again, I have one matrix here. You can use different theta or the same theta. And now here is differentiation of the frequency, differentiation of the magnitude. That's definition of inertia. Right? So if you want to, for instance, calculate differentiation of frequency of the grid, differentiation of the magnitude of the grid, which normally we don't need, but some people go to this approach. For instance, you can use EPLL because EPLL here, when you apply VG, it gives you magnitude. Before that, before that integrator, it gives you the derivative of the magnitude. Or here gives you the frequency. Before that, it gives you derivative of the frequency. Okay, now I combine everything together. I have some set points. I add static support, and I add dynamic support. And these are those matrices that I just talked about. So if my converter implements this one as the reference, receives this as a reference, and can give me these powers, this converter now is grid supportive. If the converter can provide these powers for me, it provides static support and provides dynamic support. Okay. So one way of implementing this grid support is if you have a controller that already designed that follows P set and Q set very quickly, just calculate all these things using PLL or whatever thing you can and give this as the set point and it will follow. So it will be grid supportive. But that is not very common, and you will see the more why it's not common. The better way is to use this approach that I'm going to talk about. It's called virtual synchronous machine. Now, virtual synchronous machine, people derive its equations from different ways, from different approaches. Some people try to mimic the equations of the synchronous generator. And the approach that I have taken here is very different. It's basically based on this very concept. I want my converter to provide this one. So let's calculate this term versus the others. So you will end up with this equation. Okay? And specifically, if theta D is equal to theta S, this matrix, for simplicity, it's not necessary. This matrix will go away, right? And now, what does this mean? This means if I have a system that can implement these equations, if my inverter implements these equations in its structure, it will be grid supportive. So what I do, I take P set and P, subtract them, Q set, Q, subtract them, pass through this matrix, plus this one and this one, okay, and then integrate them. So divide by KFD, divide by KVD, and then I didn't continue using the same terminology. I use the terminology that people in VSM use. 1 over J omega S and 1 over M. If you integrate them, one of them gives you frequency, one of them gives you magnitude. So these are the internal frequency and integral magnitude of the converter, voltage of the converter. Once you have frequency, you integrate the frequency, it gives you phase angle, and then cosine of that phase angle multiplied into V, that gives you voltage. If your converter implements this thing and generates this voltage at its terminal, it has implemented these equations and it has implemented the grid support functions. And if you go and write down the equations of synchronous machine and try to copy them, you will end to the same point. However, there you don't have this matrix. This matrix is just unity in synchronous machine. Okay. Yeah. Right. That's right. That's right. That's right. Okay. So these are the governor and AVR functions in the synchronous machine. This is the inertia for the real power. This is inertia for the reactive power. Yeah, and this is the internal voltage of the machine. Now, this is the internal voltage of the machine. The next step is what is the synchronous reactance? We haven't talked about that. We'll talk about that. So for the synchronous reactance, So this voltage minus the grid voltage between these two is the synchronous reactance. So that will be this one. And it's an inductor plus resistor. With the difference here that in synchronous machine you do not have control over choosing these two, but here you can really choose LV and RV, virtual resistance and virtual inductance. So another good thing is that once you pass this one, this minus this one, through this block, that gives you the reference for the current. And now you can limit that reference properly, and then current feedback loop. Everything is done. We generated a reference current, and then we limited the reference current using current feedback loop, and we made sure that the grid support functions are achieved. For the limiting case, we cannot, as we said before, we cannot limit directly a sinusoidal function because you will clip that function. So what we need to do, we need to limit in the DQ domain. So you need to convert the equations of this part to DQ domain and then limit in that domain and then come back to the sinusoidal domain. So we go to DQ domain and then we limit in the DQ domain with the same mechanism that we just discussed in the previous discussion, and then gives you the reference current. And whenever you want to generate here VGD and VGQ, you can use this approach here to generate that. And you use the angle phi, which is the angle of the machine, or converter basically, this angle here. So if you look at this structure, we don't use PLL at all. For PLL needed angle, we use PLL to provide us the angle and frequency and the magnitude. Here it's not necessary. So we can use the same angle because we know that this angle will follow the grid angle anyway. So we use the same angle for transformation. And the current control loop is this one. We already discussed how to design it, no problem. Okay, grid voltage magnitude. This is the way to calculate real power and reactive power. This is the way to calculate, no problem. And stability analysis. Now, this part I'm going to skip because it's going to take a lot of time and it's not necessary. I don't know if I already skipped or no. Probably I did. It was 58. No, I didn't. So read through that stability analysis. If you are really interested in mathematics of this, there is still a lot of room for research at the graduate level for the stability analysis of VSMs and mathematical modeling of VSMs and these things like that. Particularly, one of the things we proved is that if you add a block here and call it D and add it here, it will significantly improve the stability of VSM. And then we showed by equations why this happens and some details. Even we have separate paper on this, so you can look at that. And the equations are here. And once you do a stability analysis, during the stability analysis, you can find how to design the parameters. Here the parameters that you have is this D and this M. J will be the moment of inertia. That's the point I told you before. In DC, we did not have clear indication of how to choose J or that capacitor. We call it emulated capacitor. But here, J represents the moment of inertia in AC, right? We know moment of inertia of the machines which are out there, especially the large machines for three-phase, not for single-phase, right? So, but anyway, based on the information we have from actual machines, we can choose J. So the control parameters are J, which is kind of clear, D and M, which I will discuss a little bit, and this RV and LV, this synchronous reactance. So the stability analysis eventually, after all these equations, which I'm not going to go through, a lot of root locus and these things, I'm going to pass. Yeah. Tells you how to design these parameters. Design of J, I explained again here how to do this. One aspect of this VSM is the starting synchronization. Starting because we don't have PLL. We don't. If you want to really bring a PLL also to help for the starting synchronization, it's good. But otherwise, there are different mechanisms to start the system. One of them is explained here. And then now this VSM, if you look at the whole mechanism, it generates a voltage regarding your question that you asked before. So it's actually a voltage source. It's not even current controlled voltage source. So it's a voltage source. It can form a grid, no problem. And it has supportive functions. So if there is a situation like this, that you have grid and load, and this switch can open and close, and you have a VSM controller on this converter, it should work. It will not have any problem. However, one aspect remains that when it is disconnected from the power grid and wants to connect to the grid, just prior to that connection, you need to make sure that this voltage and this voltage are synchronized. Right? In DC, already I talked about that, but it was not very crucial in DC because the voltages are already very close in DC. But in AC, because they are changing, it could be very extreme. One of them on the positive peak, one of them on the negative peak, and then if you close the switch, will be dangerous. So you want to make sure that this voltage and this voltage are closely synchronized before you close the switch. That is called grid connection synchronization. Again, there are different approaches, but what we did in our system or this controller is this one. So you take VGD minus VSD, these two voltages on the DQ domain and the DQ domain, and then limit them because they can become very large, and then add to the set point of real power and reactive power. So by doing that, you are asking the converter to change or adjust temporarily its real power and reactive power to make sure that these two voltages go closer to each other. So whenever you want to connect to the grid, sometime before that, you enable this block, and then we'll push these we'll push its voltage, the converter will push its voltage to become closer to the grid voltage, and when they are sufficiently close, you can close the switch. This is a simulation that I have here. So starting synchronization during time 0 and 0.1. Inverter starts at t equals 0.1. And then reactive power set points, real and reactive power set points at 0.5, low voltage grid fault and fault. So all of them in grid connected mode. This is the grid connected situation. So here is the starting time that the inverter is not working, but you are synchronizing to the grid. And then after the synchronization is done, you start your inverter. Set points are 0, so the current will be 0. And then set point of real power to 2 kilowatt. Set point of reactive power to 2 kilowatt, negative 2 kilowatt, again back. And then grid voltage fault. So we actually managed to follow the set points. Right? These are internal variables of the VSM. They are called internal variables, or they are called virtual frequency, virtual voltage. Even they are sometimes called virtual speed and virtual voltage. This situation is that you disconnect from the grid. So transition from grid connected to a standalone at time 0.08, right? So you disconnect from the grid. There is a load there, so now the converter will power the load. So the current will go down a little bit to make sure that it provides the required voltage for the load. The voltage remains almost the same magnitude, however, it starts changing the angle because the grid is no longer there, so it starts shifting. If you look at its frequency will keep going up until about 61 hertz because the load is small. So it uses a droop like a synchronous machine. If the load is small, the frequency goes up. Now we want to reconnect back to the grid. Before reconnecting back to the grid, at this point, let's say at 1.2, you need to enable the synchronization block. So when you enable the synchronization block, this VGD and VGQ, which is this one and this one, go closer, sorry, this one and this one, come closer to VSD and VSQ. So because we are doing with the angle of the synchronous machine, so from synchronous machine perspective, the grid is going away, right? So it brings the grid closer to itself. So it will push the grid back to itself. Now here you are safe to connect back because these are closer. And even if you look at the voltage, you see these two voltages will go closer and closer. Now it's safe to reconnect back and then smooth transition, and the frequency will go back to 60. This scenario is now wants to show the grid support function for this converter. I think only 2 minutes, I will finish this one. So here is when the grid frequency changes, go up, down. So this is disturbance on the grid frequency. So the frequency goes up, the converter reduces its power. And then when the frequency goes down, it increases its power. However, I think I chose theta equal 45 degrees in this simulation. So both real and reactive powers are combined. So it provides both combination. It's not only in real power, also in reactive power. If I choose 0 degrees, you only see real powers. And also for the magnitude, again, because it's 45 degrees, when the magnitude goes down, it provides more real power and also more reactive power. That's it. Let me see. Simulations. Do we need to do anything? Class 9. I think that I don't have a simulation to show for. We have simulation. This is the same simulation we could show, but I don't think I have its file. Oh yes, I do. See. Let me close the other one. Hopefully, if it comes up quickly, I can show that. Or just to save time, it's not really important. You have the files, you can run on your own, and if you have any questions, let me know. It's just standard files, similar to those standard files that we have had. Oh, it came up, so let's quickly look at it. I thought it may take a long time. So the power circuit is the same as before. We have a single phase inverter. Here is DC voltage and inductor and a load. Whenever you have a load, I said you need to have some capacitors. And then connected to the grid. So this switch connects and disconnects from the grid. So as far as this is the PWM part, this is the current controller part, this is the VSM, core VSM part, and this is the current limiting part. Okay. And this blocks just to calculate real power, reactive power, bring it here. Right. This is the grid synchronization part. And a lot of these blocks are for display and saving. So display and saving here and there. The running of the entire simulation probably takes a few minutes because I ran it for a long time to get all those frequency disturbances and the magnitude disturbances, those take, but let's at least look at some parts, initial parts of that. No, we don't change anything. We only add one more term to the power set points such that, yeah, we don't want to change anything else. Just add one additional term to make sure this voltage moves towards that one. Okay, so this is the scenario. You see, time is 6 seconds now. All the other simulations we ran before, they were in the order of fraction of a second. This time is much longer. But because I wanted to run all these cases that I showed you in multiple figures in one simulation. So here is the point that you apply initial set point, for instance, power set point, real power, reactive power. And this is in grid connected mode all the way up to, I think, 0.8 or something. Different disturbances in grid connected mode will be real power, reactive power, grid voltage fault, and these things. I think here is when it's disconnected from the grid at 0.8, I believe. Yeah, it was a little transient. See, it's the transient because you disconnected from the grid. And you can see it here. Now, VSD and VSQ start going off. So these remain the same, even though they become noisy because grid is no longer there. But the grid voltage, from the perspective of the machine or inverter point, the grid voltage will keep going off. These are the set points that during the grid connected region, they follow the set points. Now at 0.2, we enable the synchronization. So when you enable, it will push those two voltages towards this one. See, he will push this one towards this one, and this one towards this. And now when you are sufficiently close, here you can close the switch and connect to the grid. So the voltages become exactly equal, and the transition should be good. So this is the transient that you get at the transition. Yeah, very smooth. And now when it goes to grid connected mode, I will apply those two big disturbances, frequency disturbance and magnitude disturbance. So I think first frequency goes, I don't know which one. But anyway, those two disturbances will be applied. We can stop the class here and continue tomorrow morning. I don't know if there is time for questions. Anybody has any important question? Because I think we are over the time. Any urgent question or anything? If not, we can stop here.